Carpe Diem VPN. Seize the network.
Hey everyone, it's Tim with Carpe Diem VPN. I wanted to put my SD-WAN stuff on hold for just a little while because I just ran an SD Access CPOC lab with a large customer, and I still have the lab live for another half a week or so. So I wanted to show everybody how SD Access works at a basic level, kind of why you would use it, and what we did in our CPOC. So here I've got a diagram of the lab set up. Let me go ahead and switch over to that. Okay, so this looks like a lot. It's very complicated. Don't worry about it too much. The naming convention has to do with the racks inside the CPOC lab where the gear lives. So you can see a majority of this lab was built in the cheese rack, for example. Let's just go over kind of orient ourselves around the lab and see how it's set up. So here we have a mock data center. We've built it using a Stackwise Virtual 9500s as the kind of core of this data center. Over here we've got two Catalyst 9800 wireless LAN controllers in kind of an active failover mode. Down here we have three Cisco DNA Center appliances that are clustered together. And then we have several UCS chassis which are providing us virtual services. So we have ICE built there, some Active Directory servers, DHCP, DNS, so on and so forth. Cross-connected over to the side is our services aggregation layer. That's where we have two ASR 1002 HXs working to kind of connect the campus to the data center, and then northbound we have a pair of Firepowers running ASA code as our internet edge. And of course down here is our SD Access fabric. We're using Cheese 6 and 7 as our border and control plane nodes for the fabric. Cheese 12, 13, 14, and 3 are acting as our fabric edge nodes and connected to users and devices. And the distribution layer with 10, 11, 4, and 5 are just providing underlay connectivity. So we're switching over the top of those. They don't have an actual fabric role, but they are part of the fabric. Between the data center and the aggregation layer, we're running a iBGP neighborship, BGP AS 65010. And then southbound, between the ASRs and the border nodes for the fabric, we're running eBGP, and the fabric's running BGP AS 65020. Now within the fabric itself, of course, we're using Lisp as the control plane. So with Lisp, the edge nodes are going to advertise host bindings to the control plane nodes to register with the Lisp map server. And if you don't understand Lisp, it's not a big deal right now. I'll kind of cover it a little bit in this video, but I'll make another video where we cover Lisp at a much deeper level. But understand that Lisp basically works kind of like DNS. So it's not so much a routing protocol as it is kind of a host registration protocol in how we're using it in SD Access. The switch that's attached to the host will register the host binding with the map servers, and then when people want to reach the host, they'll query the map servers and say, okay, well, which switch are we connected to? So that's very, very high level, but think of it like that. And we're running a different Lisp instance for each virtual network. And a virtual network can be just thought of as a VRF. So you can see in this case we've got 3 different virtual networks running, and what the control and border nodes are going to do is, or rather what the border nodes will do, is aggregate those Lisp routes. So remember, we're sending kind of host bindings, so /32 routes. Lisp will actually aggregate those host routes into a BGP aggregate and then advertise it per VRF or per VN to what's called the fusion routers, which are the routers off of the fabric, which are not part of the fabric. They're BGP peered with the border nodes. They're peering on a per VN or VRF basis. And then the fusion routers, in this particular instance, are going to fuse all of those VNs into a global routing table because they're not running VRF, and advertise that to the data center. At the same time, the services layer from the firewalls are advertising a default route both to the data center and down to the SD access fabric. Well, we haven't built the fabric yet, but this is how it's going to work once it's all configured. So this is the routing design, if you will, for the fabric. The data center is going to advertise the data center routes to the aggregation services layer, which will then turn around and advertise it to the SD access fabric. So where are we at before we start deploying the fabric? What does it look like right now? So right now we have our DNA center running, ICE is configured, Active Directory is configured with DHCP scopes. Our data center core is working. It's stacked in a stackwise virtual configuration. Our WLCs are up, although they're not connected to DNA center yet, or to a fabric, because the fabric doesn't exist yet. And then over on the right, you can see with the services layer, Charlie 16 and 17 are connected to Cheese 6 and 7, and there's a peering that's happening there. Before we zoom in on that, you can see southbound of Cheese 6 and 7, all of the switches that are going to be part of our SD access fabric have no configuration, and they are in fact in plug-and-play mode. So they're waiting to be configured using LAN automation. So taking a closer look at how we're configured on between the services layer and the border nodes, right now, before we deploy a fabric, just for reachability, we're peering Cheese 6 and Cheese 7 with Charlie 16 and 17, and they're doing it with crosslinks and 2 different VLANs. And this is just eBGP, so that the DNA center can reach these devices and control them. Now, before we start building our fabric, I think it's important that we talk about what problems a fabric solves. So is SD access a solution in search of a problem, or are there actual business use cases and needs and problems that SD access is solving? I think that's a huge question, especially for somebody who's thinking about whether or not they need to adopt it. For people who are studying it for a certification, maybe design isn't quite as important, but I promise it is very important to understand what problems we're solving with SD access, because at least in my opinion, we can't really understand a solution until we understand the problem that we're trying to solve. So let's just kind of talk a little bit about what problems are we solving. So in a normal campus, this normal campus setup is pretty common. It's that 3-tier model. This might be the core here, Cheese 6, Cheese 7 might be the core. We might fan out to a bunch of distribution switches, 10, 11, 4, and 5, and then they'll be cross-connected to switches at the edge where our users live. So that's pretty common design. There's a couple ways to do it. Normally, again, it depends on what features you have and what your strategy is, but it's still fairly common to see. So something like Cheese 12 would be a layer 2 switch, and then these would be trunks up to here to the distros. The distros might be running, HSRP between them, and then that's their layer 3 gateway for the users attached to the switch, and you'd run multiple VLANs. So say if this guy was a corporate user and this guy was a security user, or maybe he was in in a PCI VLAN that could be interacting with credit card data. You'd put them in different VLANs, and then we'd go up to the 1011 here, would again run HSRP and have our VLAN interface for both VLANs. And what are the challenges there? And so now we have a challenge of segmentation right out of the gate. And this is a normal design. So how do we segment our PCI user from our corporate user? How do we keep our corporate user from accessing or attacking our PCI users and stealing credit card data? Well, I mean, in this setup, we're kind of limited. So we could put an access list. We could put an ACL. We could put an ACL that targets the PCI VLAN, stops it from from anybody from talking to that VLAN. But now we're relying on IP addressing. We have to create an IP ACL. We have to attach it to that PCI layer 3 VLAN that's shared between these switches. If anybody we're able to pull an IP that's allowed to talk to it. They can get through. It's just not very good. So, that's the first kind of thought of what are some of the problems that SDAccess can solve for us. Now, this is a problem that can be solved even by Cisco TrustSec, which is of course part of SDAccess, but it's its own solution as well. We can do ICE enforcement, downloadable ACLs. We can apply SGTs based on identity services. That solution we already have, and that can be configured in ICE. But when we make it part of the SDAccess fabric, that's just enforcing microsegmentation as part of the fabric. So it's one solution. It's one part of the solution. So let's get back to the problems that we're solving. So okay, so let's say, all right, so let's erase this. Let's go back. Let's erase all this and say that we don't do layer 2 access. Maybe we do routed access. So routed access means that we're running a layer 3 switch, and now that means that every VLAN that exists per switch, or every subnet really. The VLANs can be reused because we're not worried about spanning tree. So let's say, okay, so for the corporate user now, let's say on this switch, we're going to use 10.1.1.0/24. Now, because this is routed access, all the users here, they can't overlap with other switches. So on this switch for a corporate user, we're going to have to use 10.1.2. And excuse my ghetto, my not very good annotation here. I don't have a Surface. I was going to buy one, but then this whole COVID thing hit, so I'm holding off for now. But the idea with routed access, again, is that per VLAN or per subnet, per switch, you're allocating IP addressing. So here's my corp user 10.1.1, and maybe my PCI user is going to be on this switch, 10.1.5 or something. And then over here, if I have a PCI user, it'll be 10.1.6. And you see that very quickly we've eliminated the spanning tree problems, but we've introduced an IP address design issue, a potential issue. Because for every one of these subnets that exists, if these are 40 closets, you've got to allocate IP addressing. And then if we want to enforce security, let's say we don't have TrustSec. Let's say we only have, we need to force through, say, a firewall in order for the corporate user to communicate with the PCI user, or rather to stop it from happening. Or, there's a lot of challenges there. Maybe the PCI user needs to go through a firewall to talk to anybody, and anybody needs to go through a firewall to talk to the PCI user. Say there's, some kind of credit card server in the data center, and, the PCI user needs to be able to reach that, but we don't want our corporate user to reach that. So again, the point is we want to be able to force traffic through a firewall in order to enforce security. So now we have to somehow segment the traffic at a layer 3 level all the way up until we hit a firewall. So how are we going to do that? Well, we're going to do that probably with VRF Lite. Now VRF Lite, as for anybody who's ever configured a VRF Lite, it's not that it's complicated, but it's cumbersome, especially if you're doing it per VRF. Let's say we have a PCI VRF, and so on this switch we have a corp VRF and we have a PCI VRF. And we have a corp VRF and a PCI VRF, and on down the case. And so what that means now is that when we peer at layer 3 with our upstream switches, we have to do it, using, say, sub interfaces, or we have to allocate actual interfaces, which nobody's going to do that. It's going to be sub interfaces, And so now we're running sub interfaces per VRF. We got extra IP addressing, we've got extra complexity, and that's per switch, per intermediary device. So now Cheese 10 in this situation has to have 3 different VRFs configured on it, and then when it uplinks to Cheese 6, it has to do it with sub interfaces, and that's to maintain that layer 3 segmentation all the way up. So now Cheese 6 has to run 3 different VRFs. And when it peers with the ASRs, it's going to peer over 3 different VRFs. And ultimately, all of that's going to be preserved until we hit our enforcement layer, our security enforcement layer, which is our firewalls. And this is a ton of configuration to do this. It's an option. It's a way to solve the problem, but as you can see, it can become incredibly cumbersome, especially if we're scaling this out to 100 switches or something like that, and then upstream. So what problem does SDAccess solve for us? Because we have, VXLAN, we have the ability to do tunneling and preserve a lot of that segmentation without having to increase the amount of intermediate configuration. We can just ride over the top. Kind of, if you think like DMVPN, it's a little bit like that. I mean, it's not technically like that, but if you can think of it in the idea that we're just kind of passenger riding over infrastructure, the infrastructure doesn't need to be, or MPLS. Actually, MPLS is probably a better example. With your P routers, they don't have to be VRF aware. They don't have to even be participating in the BGP that carries the user routes, if you will, or the VPN v4 routes over the top. So it's a little bit like that. Think of it like that, but without having to actually run MPLS. We're using Lisp as the control plane for where our tunnel endpoints, and we're saying with VXLAN, we're going to route between our tunnel endpoints. And we're going to go right over the top of the infrastructure without having to configure VRF Lite all over the place. So that, again, is a problem that we're solving with SDAccess fabrics. So let me remove all this, take a minute. So, and because we're doing this, because we're able to simplify this part, there's some other options, right? So we have routed access without having to extend VRF all the way to an enforcement point. We also have the ability, using in an SDAccess fabric, to simplify our IP addressing design because we have the ability to do Anycast gateway. So what does Anycast gateway mean? It means, like, for example, for this VRF, let's say our Corp VRF, this guy, Corp VRF, they can all use the same layer 3 gateway, and it'll be 10.1.1, and it'll be the same on every switch, 10.1.1, 10.1.1, right? And that's what we call an Anycast gateway. Now, how does this work? How can this possibly work? So without getting too far into the weeds yet, again, it has to do with our Lisp control plane, because with Lisp, when our host connects and gets DHCP from the DHCP scope, its gateway is set to a VLAN interface, and it's the same VLAN interface you'll notice on all three, or four actually. I guess this one's the same as well. These Anycast gateways all share a MAC address, but again, it's really only invoked at a layer 2 level. What's happening is that the MAC or the client is registering with the Anycast gateway, and then this device, this edge node, is registering that host map using Lisp with the control plane nodes, and it's saying, I am switch X, host Y is connected to me. So if anybody needs to route to that host, this is how they do it. So that's how we can have an Anycast gateway, because the switches themselves are registering the hosts with the map servers. So again, I didn't want to go too far in the weeds, and there's obviously there's some technical clarity there. But again, I'm trying to keep this part more of a high level because we're talking about what are the problems that we're solving. So we can vastly simplify our IP addressing design because we don't need to allocate subnets per switch per VLAN, so on and so forth. You can actually take an entire VN and just assign it one block of IP addresses, because remember, we're not doing layer 2 everywhere, right? We don't have a giant broadcast domain. We just are using the VNs to route, basically. So you'll see in the lab that I'm building, I use 10.1.0.0/16 for the corporate users VN, and that's completely supported, and that simplifies any kind of firewall design, any kind of firewall rules, any kind of security enforcement outside of the fabric that we would need to do as well. Of course, it also simplifies it within the fabric. Using things like ICE, we can profile our devices using .1x and, say, hey, this user belongs in the corporate VN. Bam, ICE sends profiles the port or sends a VLAN change of authorization and everything to the port and changes it to that VLAN. And now it belongs in the corporate VM. So we're not replacing networking. It's not a black box or anything like that. All the networking still works the same way as it always did. We're just allowing a controller to configure it for us, and we are so obfuscating a little bit by using VXLAN and Lisp there. So what are some of the other problems that we're solving, right? So the microsegmentation policy I just talked about, right? So we can have an SGT of, say, corp attached to a corporate user, and we can enforce that within the fabric. So a corp user can't talk to a PCI user, even though the routing might be there. Or let's say for some reason a PCI user connects to the switch, and they're placed in the same virtual network for some reason, but their SGT says PCI. So we have the ability within the fabric to block two people that are in the same VLAN, the same subnet, without any IP ACLs or VACLs or DACLs. We're able to stop these from communicating without having to build firewalls into every layer of our network. That's another huge benefit of TrustSec in general, but how TrustSec is built into the SD Access fabric. So you can see there's a lot of benefit to having an SD Access fabric, microsegmentation, simplified design, simplified IP addressing. And a lot of people are like, oh, but it's super complicated. It's a very complicated design just to get these benefits. And I would posit that it's not that it's super complicated. I don't think that it's super complicated. I think it's different. It's different than all of us as engineers know already. Very few enterprise engineers knew Lisp before SDAccess started using it as the control plane. I think Lisp is incredibly cool. It has a lot of utility well outside of the SDAccess world. But let's face it, it wasn't in our toolkit beforehand. And I also think, VXLAN, what we're doing in the data plane with VXLAN is very cool. Again, a lot of us enterprise people don't know VXLAN, so it's new, it's scary, we don't understand it. The implementation of it is actually a little different than you would see even in the data center, right? With BGP, VPN, it's a completely separate setup. It's totally different. Instead of using VNIs and VNEs, in the data center as our VXLAN endpoints, we're using our RLOCs, which is our routing locators, our Lisp routing locators for the tunnel endpoints. So there's a lot of difference there as well, and that makes it scary, and that makes it complicated, or at least makes it look complicated. And I'm not saying there's no complexity here. Obviously, this is still a complex design. That's why we have a DNA center to deploy the configuration, and that's all the DNA center does, is deploy the configuration. The DNA center is not a magic black box. The DNA center translates our button clicks or our API calls into an actual config that we're going to provision to these devices, and I'm going to show you that as part of when we do LAN automation and when we do fabric deployment. You'll see that there's no magic that's happening. It's just the controller translating our clicks and our intent into an actual device config. I think that's the biggest thing people are afraid of with SDA and with DNA Center, is this idea that it's a black box that lives on our network and it just does stuff. It waves its hands, it does wibbly wobbly, timey-wimey stuff, and all of a sudden we have a fabric, and that's just not the case, and I can demonstrate that. So now I think we're probably ready to move into LAN automation. Again, LAN automation is a greenfield type of solution where all our devices that we're going to build into the fabric are sitting there. They're waiting to be connected, or rather to be down part of the fabric. They're ready to be bootstrapped. Sorry, that's the word I was looking for. They're ready to be bootstrapped via PnP to DNA Center, and for DNA Center to provision an underlay for us. And that underlay with LAN automation is going to be ISIS. Again, that's something else that kind of terrifies us enterprise people. Probably doesn't scare anybody in the SP world, but it's new, it's different, it wasn't part of our toolkit, and so that's scary. But you'll see that the way ISIS is deployed is actually far simpler than you probably think, and works very similar to OSPF in the way that we're using it. Okay, so let's, without further ado, we'll get going on building a fabric. Let me just show you how that works, and we'll look at the config and everything